Okay, today, we're going to start the chapter 3, matrix and matrix algebra. We will cover first three sections in this week. Okay, first, matrix, as you know, matrix is widely used as a tool to transmit digital sound and image through internet, as well as solving linear systems. Okay. In this chapter, we define addition and product of two matrices. These operations are tools to solve various linear systems of equations. And matrix product also become an excellent tool in dealing with function composition. Okay. In chapter 2, we have found the solution set using the Gaussian elimination. In this chapter, we define the addition and scalar multiplication of matrices and introduce algebraic properties of matrix operations. It will be used to describe the relation between solution set and matrix. Furthermore, we investigate the concept such as linear independence and subspace. Finally, we introduce some interesting special matrices. Okay, and here are some mathematicians who made great contributions in these matrix operations. First, section 3.1, matrix operation. In this chapter, we introduce the definition of the addition and scalar multiplication of matrices and algebraic properties of the matrix operation. Okay, equality of matrices. Two matrices of same size are equal if all components are same for all I and j. In this case, we denote these two matrices equal, like this. So, suppose these two matrices A and B are equal, then what are the value of this x, y, g, and w? This should be, w should be -1, and x should be -3, and y should be 0, and g should be 5. So it's and additions and scalar multiplication of matrix, scalar multiple addition. The addition of these two matrices are just those. Each entries of each ij's entries of A plus B is consist of the addition of ij's entry of A and ij's entry of B. It's like this. The size of this matrix is same as the size of matrix of A and B. These should be the same size, m by n and m by n. Those two matrices should have the same size. And Ka is defined that each component is consist of the case multiple of the Aij, which is Ij entry of the matrix A. Okay. So suppose we have this matrix A, B, C, then the addition and scalar multiple can be found in this way. Just by adding these two, 1 plus 0 is 1, 2 plus 1 is 3, so like this, and 2a. So that's what you know. And this can be done in here, matrix operations, like this. Control C. Here. Okay, so if we have a two matrix like this, then here, suppose we have a two matrix like this, then this the computation can be done in this way, and the code are this: A plus B, 2A minus 1C can be found in this way, which is same as the matrix that we have found. Like you see here, 2, 4 minus 8 minus 4, 2, 6, like this. If we change the numbers here, then we will have a different answers like this. If we change the size of these matrices, then this computation also work for those if the size of two matrices are same. Okay. Okay, so for this example, yeah, if you can just copy this to practice in the website that I supplied. The first important thing is that this matrix product. Given two matrix A and B, the product AB of A and B is defined as below. Here, the ijth entry of AB is this, like this. Summation of AI1 B1j plus AI2 B2j AIP times BPJ, like this. This is summation of AIK times BKJ from K is equal to 1 to P. Okay. Product of AB. So this is very important and interesting definition of the matrix product. In here, the size of the number of column of A should be same as the number of rows of the second matrix B. So this should be matched. Then the size of the final matrix should be the number of m by n, which is the size of the number of rows of A and number of columns of B, respectively. The meaning of this matrix product. Suppose the matrix product of A and B, which is C, can be written in this way. The product of the matrix with these rows and the columns like this. Then the ijth entries of this matrix must be ith row of this matrix times the column, jth column of this matrix. So Cij is a ith row times the of A times jth column of the matrix B, which is this, the summation of A1, I1, B1J, and I2, B2J, like this. So this is the definition. So simply the ijth entry of AB is the inner product of ith row vector of A and the jth column vector of B. That is it. Which is this? ijth entry of AB is the ith row times jth column of the matrix B. Okay, so yeah, someone called this is a King Sejong's rule. So suppose you have two matrix A and B, then find the product of those two matrices. So you just fill out the 1-1 entry, 1-2 entry, and 2-1 entry, and 2-2 entry like this. And you can do the computation simply by just giving the A times B, A star B, will give you the same answers like this, even for the large size matrix. Okay, using this matrix product, one can express a linear system in this way. A, X, B, then this linear system of equation can be written as AX is equal to B, which is this is equivalent to this B vector can be written as a linear combination of these vectors. Okay, which is equivalent to, right, this x1 times this plus x2 times this, xn times this, like this. So this is a very interesting notation and also equivalent statement for many possible questions related to this matrix representation of the linear system of equation. And the first theorem here. Suppose we have a three matrix A, B, and C of the proper size, then the following holds. The matrices are commutative under the addition and the matrix addition, and associative under the addition, and associative law work for the matrix multiplication, and distributive law works like this. Okay, so these are the familiar rule that you already know. It's very easy to compute. All you have to do is to check the ijth entry of the left-hand side the same as the ijth entry of the right-hand side. That's all you have to do. Okay, check the associative law of the matrix product A, B, and C. Then you check AB and find the ABC here, and you find the A times BC. Then you will see the same, you will have the same answers, the same matrices that shows. If you randomly generate the matrix ABC of the reasonable size, then you will see it always work. Okay, most of the property of this operation on matrices are similar to those of operations of real numbers that you already know well. But there is one exception, which is this. The real numbers are commutative on the product, but matrix is not commutative on the matrix product. A, B is not always same as BA. As you see in this example, here we found the AB and we find the BA, but those are not same. Also, for the matrix D and E, if you do find the D and ED, are they same? Or not? So the matrix product is not commutative. That is very, that makes a very interesting differences. And also, this gives us interesting generalization of the product of real numbers. And the matrix computation can be done in this GeoGebra tool for simulation of this matrix computation that you can check. Also, the zero matrix, whose entries are all zeros, so the matrix whose entries are all zeros of any size are called the zero matrix. And zero matrix hold these properties. If you add zero matrix on any matrix, it does not change. And subtract a same matrix from a given, then the result is a zero matrix. And the product of zero matrix on any arbitrary matrix A is also a zero matrix. This is also another interesting factor. Even though AC is equal to AC and A is not zero, but still B and C can be same. Yeah, so this shows a generalization of the real numbers in a high-dimensional vector space. Identity matrix, yeah, this matrix, a matrix whose all the main diagonal entries are 1 and all the off-diagonal entries are 0. We call the identity matrix. In this case, we call this is an identity matrix of order n, and we denote it by I sub n. And the identity matrix satisfies these properties. If you multiply any matrix on the identity matrix, it stays there. So it does not make any changes. Okay, suppose A is this, and then IA is the same as A, and AI3 is equal to A. In here, we multiplied 2 by 2 identity matrix here, and we should have a 3 by 3 matrix here to have a matrix product. So we have a suitable size of the matrix to multiply on left and right side. So in here, so yeah, you can easily check if give the any size of matrix, multiply the identity matrix of size 2 on the right, on the left, and multiply the identity matrix of size 3 on the right hand side, then you will have 3 by 2 matrix which are same like this. 그러니까 여기에서 okay, and if you subtract zero matrix, and the power, case power of matrix A can be defined in this way, and the product of the matrix can be have this property. The R's power of A times S's power of A can be the same as the R plus S power of A, and the S power of the R's power of A is same as RS power of a matrix A. This is an important property as well. So suppose we have a matrix A, then we can find any powers of the matrix. So suppose we have this matrix A, which is 4, minus 2, 5, 0. Then we can compute A square, A cube, or A0 power, and A to the 6th power by using these earlier ones. Then you will see A's 0th power is always identity matrix, and this is same as this. So I checked it. So that says the left-hand side is same as right-hand side always. It's true. So that's what it gives us. Next property. The square of A plus B can be written in this way. But this is not always same as this. This is only same when we have A plus B is equal to BA. If they are not commutative, we cannot simplify it in this form. Transpose. For a matrix A, the transpose of A is denoted by A transpose here and defined by this way. The ijth entry of A transpose is same as AJI from the matrix A. Okay. So the transpose is obtained by interchanging the rows and columns of matrix A. So suppose B is like this, then what is the B transpose? Just leave the main diagonal and change 2 to here, 3 to here, minus 4 to here, 2 to here, and 5 to there like this. Just replace the rows and columns. And yeah, you can easily find the transpose matrix with this command. Transpose of A. AB matrix is of the appropriate size. The K is a scalar, then the following hold, like this. The transpose of transpose is A. The transpose of A plus B is A transpose plus B transpose. The transpose of AB is B transpose A, or B transpose times A transpose. This is very important. You should know to solve many problems. The example 10 shows AB and AB transpose and B transpose times A transpose, which is same as AB transpose. Transpose here. This is very important property that you should know. The trace of A is defined in this way. The addition of, summation of all the main diagonals. Summation of all the main diagonals. Okay, the theorem on 3.1.5 is this. Trace has these properties. Trace of A transpose is same as trace of A, and the scalar multiple came out, and it can be distributive like this, and also this one, fifth one. Trace of AB is same as trace of BA. How you to prove this one? Just think about the main diagonals of AB, and then add sum up all those main diagonals of the matrix AB, and also sum up the main diagonals of the matrix BA. Then you will see they are all same as this. So this is a very important property that you can easily check. All you have to do is just add the main diagonals of right-hand side and left-hand side to compare. Suppose we have A and B like this, then you can find the trace of AB and trace of BA, which you will see they are all same. You can check it by randomly generate the same size of matrix A and B and do the same computation to check it. I think that's the end of the section 3.1. Any questions?